Hello everyone. This is what we discussed in class today. This is section 5.4 of your book, and we started talking about logarithms, and this is a condensed explanation of what we saw in class. Just for a review, just for you, we said that the logarithm is the inverse function of the exponential function. Last week we learned about exponential functions. This week we're going to learn about logs. And the logarithm of x is the inverse function of the exponential function. Why? Because when we work with exponential functions, if I want to find the inverse of this exponential function, remember how we used to switch y for x? And let me do it here to the side. I'm going to show you very quickly. We would write y is equal to 10 to the x power. And then we would substitute y for x and x for y. Okay, and now we have to solve for y. And how do we solve for y? Well, this is written in exponential form. I can rewrite this as a logarithm, which you're going to learn how to do in this video, but just bear with me. This is what you do. This would be log base 10 of x equals y. And there you solved for y, and we always write our variable to the left. Okay? So this would be my inverse function for 10 to the x. Okay? That's why when we say that the log is the inverse function of an exponential function, that's what it means. Okay? And the same goes with e to the x. Remember I said in a previous video, e is a natural number, and it is a very, very, very long number. E is 2.718, and it's very, very long. It never ends, and it's not repeat. It doesn't repeat. The decimal expansion doesn't repeat. There's no pattern. So when that happens, we know that this means that it's an irrational number, very much like pi. Pi is an irrational number. It comes up a lot, so we use a symbol for it. We use the symbol pi. Same things with e. It comes up a lot in nature, in science, in economics, and we just use the number e as a symbol for this natural number. So since this is an exponential function, e to the x, the inverse function of any exponential function we said is log, but when it's an exponential function with base e, the natural number, then we call it the natural log. Okay? This is the natural log. And it's the inverse function of e to the x. And since they're both logs, all the properties and all the laws apply to both of them the same. And here I have a graph of the exponential function. We studied this last week. This is the exponential function a to the x. That means any number to the x, 5, 6, 10. In our case, we're doing common logarithms, which is a base 10. So this is my exponential function. Remember, we had said that all exponential functions, or the parent function, has an intercept at 0, 1. And it's increasing, and it's above the x-axis, and it approaches 0 as x approaches negative infinity, etc. When we talked about inverse functions, we know it's a reflection of this function across the y equal x line, this line here, y equal x. So it's like if I folded this paper across this line, and I reflect this curve on the other side. Okay? And that's how you get the logarithm graph, by reflecting the exponential graph across the y equal x. Okay? Now let's talk about the domain of this exponential function. We have that the domain for this function is all x's from negative infinity all the way to infinity, because I have values for the function at very large values of negative infinity, and I also have values for this function as x grows towards the positive x-axis. So my domain is all real numbers. Okay? And the range for my exponential function is from 0 And it doesn't include 0. We know that this graph never touches that horizontal asymptote, and it's from 0 all the way to positive infinity. When we talk about the domain of the log function, since this is the inverse function, then the domain and the range of the exponential function switch in the log function. So the domain of the log function is the range of the exponential function, and the range of the log function is the domain of the exponential function, which is all real numbers. Okay, and let's see that. For this log function, notice that the domain x values, I don't have any negative x values, okay? All x values go from 0, but it never touches 0, okay? This is a vertical asymptote. And I can have any x value going this way all the way to infinity. So that's my domain. And the range, well, I have values coming from negative infinity if I sweep like this across all the way to positive infinity, okay? There you have what the log function comes from. It's the inverse of an exponential function. And I have this definition for log. It says that log base b of n is equal to p if and only if b raised to the power of p is equal to n. And this is the definition of a logarithm. Only if this is true, then this is true. Okay, and let's name these parts. We call this the log. That's the log. This number here, it's a subscript. We call it the base. This value here, we call the argument. And p we call the exponent. Okay? And how do we use this definition? Well, we use this definition to change from a logarithmic expression to an exponential expression. This would be your exponential expression where you have a base raised to a power. Okay, this is your exponential expression and this is your logarithmic expression. And I have 3 examples here that I'm going to do with you. Example 1, 2, and 3, they're all logarithmic expressions, and I want you to express these as exponential expressions. So how do we do that? Well, notice it says log base b of n is equal to p. Look at what happens to the b. b becomes the b, which is the base of the logarithm. That subscript becomes the base of your exponent, and your exponent is this p, and that is equal to the argument. So let's look at that more closely. If I have the log base 2 of 8 equals 3, this is what I do. I take my base, I raise it to this exponent, and I equal it to 8. So this becomes 2 to the 3rd power equal 8. And there, you went from a logarithmic expression to an exponential expression. Let's do the second one. I have the log base 4 of 16 is equal to 2. How do I write it as an exponential expression? I take the base of the log, which is 4, I raise it to the 2nd power, and I equal that to 16. So this is what it looks like. 4 to the 2nd power equals 16. And notice that these statements are true. Okay? And for the last one, I have log base 5 of 125 equal 3. Again, take the base of the log, raise it to the exponent, and equal it to the argument. So this would be 5 to the 3rd power equals 125. So there you have it. We went from a logarithmic expression to an exponential expression. And now we're going to do the inverse. We're going to go from an exponential expression to a logarithmic expression, okay? So notice this is my exponent 2. I have my base 10, and this is my argument. Let's label these. The 10, that's your base. The 2, that's your exponent. And this is your argument. Now we saw we saw that we have log base b of n is equal to p. Okay, so let's fill these in. I have the log. What's my base? My base is 10. Okay, base 10 of n. N is your argument. So this is my argument. So log base 10 of 100 is equal to my exponent, which is p. And your exponent is 2. So there, we have rewritten an exponential expression into a logarithmic expression. Now, I want to say that whenever your log has a base 10, we don't write it. Log of 100 equals 2. Anytime you don't see a subscript in your log, that means it is 10, okay? But we never write it. Some books you'll see a 10. Most books you will not see a base written down here if it's 10, okay? So whenever you see a log written like with no subscript, just assume it is a 10, okay? Let's do the second one. I have 3 to the third power equal 27, and I want to write it as a log. So this is what you do. First thing you do, you write log. Second thing you do, what is the base? Well, this is the base, because if this is the exponent, this must be the base. So base 3. Okay, I know where the exponent goes. The exponent goes after the equal sign, and this is the argument, 27. And you can check. You can go back and say, okay, 3 raised to the power of 3 equals 27, and make sure that's what your expression says. Okay, so this would be your answer, written as a log. And for the last example, I have 4 to the negative second power equals 1 over 16. Okay, let's write it as a log. First thing you do, you write log. Second thing, your base. What is your base? 4. Third thing is, this is your exponent. So you know this equals negative 2, and then your argument, which is 1 over 16. Okay, and there you have it. You've rewritten these exponential expressions as logarithmic expressions. Okay, now a couple of things that I want to, well, just one thing. The base, when we talk about the log, when we say log base b of n equals p, b has to be greater than 0, and b cannot be equal to 1. And why, do you ask? Why does it have to be greater than 0, and why can it be 1? Well, this is why. When we were looking at exponential functions, let's suppose b is not greater than 0. Let's say, just so that you can see, I'm gonna set b equal to negative 2, okay? And let's then rewrite this log with a base of negative 2. So let's write that. Let's say log base negative 2 of n equal p. And when I rewrite this as an exponential, this would be negative 2 to the p power equals n. Now remember, we had said when we had exponential functions that this number had to be greater than 1 if it's increasing, or between 0 and 1 if it was decreasing. And we said it can't be negative, and I gave you a couple of reasons. I said, well, when I have a negative, I have to be careful that p isn't a fraction with an even denominator. I have to be careful that p, when p is equal to a half, or to a fourth, or to a sixth, because that would give me even roots. That would give me even roots of negative 2, for example. And you know that these even roots are not defined. Okay, that was one problem. And the other problem was when I use numbers that are not even roots for p, like negative 2 to the first power, that would give you negative 2, negative 2 to the second power, that would give you positive 4, negative 2 to the third power, negative 8, negative 2 to the fourth power, positive 16. So you would have a positive and negative, a positive and negative. When you try to graph that, it's very erratical. It doesn't behave well in these values. Plus, if you add in this factor where whenever p has an even denominator, which makes me have even roots, then I have undefined values. So this graph, this exponential function, when I have a base of a negative number, it doesn't behave well. So we say b has to be greater than 0. Okay, no negatives in this base. Why can't it be 1? Well, let's see. If I choose b to be 1, b to b. Okay, if I choose b equal to 1, let's write the log. Log base 1 of n equal p. Then if I write this as an exponential expression, this would be 1 raised to the power of p is equal to n. And what happens with this is no longer an exponential function because p can be any value. Whenever p is 1, then this is equal to 1. When p is 2, this is still equal to 1. When p is 3, still equal to 1. When p is 1,000, that's 1 times 1 times 1 times 1 times 1, 1,000 times, it's still equal to 1. So this becomes a constant function. Therefore, I lose my exponential function. That's why b cannot be 1. Okay, so make sure you keep this in mind. Okay, b has to be greater than 0, no negative numbers, and it cannot be 1. Well, I hope you understood these examples. I'm going to do another video with more examples, just so that you can go over them if you need to, okay? I will see you in my next video.